Very kind introduction. My name is Timm from Lund University in Sweden. And here today I want to share with you our work as we characterize semiconductor nanostructures with surface science methods such as scanning tunneling microscopy. So I hope that I can show you how we can convert these methods, which are principally made for flat surfaces, use them here in this case even for complex nanostructures, even in device configuration. So we're at Lund University, we have a very strong research focus on nanowires, semiconductor nanowires. So that is, these are single crystalline rods, like you can see here. They can grow on random positions or also in nice areas, as you have here. Nanostructure rods or nanowires in this case means we have diameters between 20 nanometers and something like 100, 200 nanometers. And the length can vary between a few hundred nanometers up to several micrometers. And in our case here in Lund, we choose materials from group 3 and group 5 so that we have alloys such as indium arsenide, gallium arsenide, also nitrides for growing these structures. And with these 3-5 semiconductors comes along that we have a variety of applications, mostly in electronics and optoelectronics. That's what I will focus on with here today. But also in fundamental studies like quantum physics. You can see here an example from single electron tunneling, or even from interfaces between semiconductors and superconductors, but also within nanobiology, medicine. This is a nanowire here interacting with a biological cell. As I said, I will mostly focus on nanowires, which are then intended to be used in electronics, like for transistors, or in optoelectronics, like for solar cells or LED structures here. So how is this relevant? Why are the semiconductor nanowires interesting for this? Let me show you one example here. And this slide is not from me. It's from a well-known semiconductor company, Applied Materials, where they project the possible paths for next generation semiconductor structures, in this case here for transistors, as we are already several years ago went from a planar geometry to this three-dimensional structures that we have nowadays computers with these FinFET geometries, which are still at the limit of getting scaled further down, also due to heat processes, heat losses. So they project that in the future, the pathway for transistors should include something what is called a gate-all-around structure, so that you have the active channel completely buried by the oxide around, or that you go to 3-5 materials to reach a better, higher electron mobility or hole mobility, and be able to tune the applied voltage, to tune the band gap, so that you don't have so much heat loss due to unnecessarily high voltages, or to go to advanced structures, not just the classical field effect transistor, but for example, tunnel field effect transistors. And all these concepts can well be realized with such semiconductor nanowires, which by their nature already have these three-dimensional structure. If they are used as a channel for the transistor, the gate material will automatically be all around, as seen here in the sketch or in the SEM image here. And nowadays they are also prototypes have been grown and processed with record performance in the tunnel field effect transistor geometry, where we have a nanowire here at the bottom, which is made of indium arsenide, only 20 nanometers thin. This is an SEM image of that. And then there's a different material with hole conductance, in this case gallium antimonide on top, and you have the tunnel junction in here. As I said, these devices already have a very impressive performance, as they also have low power consumption. They have a very high carry mobility. They have a steep on-off switching, which is needed for such tunnel devices. But the main challenge, or one of the challenges, is still to improve the surface of the semiconductor, and with that the interface to the oxide material. So surface characterization is really needed here in this case. And that is the same for a different, very promising area of application, and that is towards solar cells. Why are nanowires so promising here? Well, due to their size and structure, that they can then stand upright on the substrate, they work as antennas, so they can get a very strong light absorption. focus the light into the semiconductor material, let us get a strong light absorption and convert it into electricity. So there are some examples already some years ago of this SEM image here, where we have an PIN structure. So the p-doped area, the intrinsic area, the n-doped area, all realized in an indium phosphide nanowire with the contacts on top and in the bottom, working as a solar cell. And these materials here, these nanowires, have a very small footprint, which make it possible to stack different materials directly on top of each other. So these 3-5 materials can be grown directly on silicon, or you can realize something like tandem solar cells by stacking different bandgap materials on top of each other. That is something which is ongoing also right now. But also here, the main challenge is not so much the p-n junction itself, but rather the losses that happen here at the surface. How can the surface be passivated to avoid losses at the junction? So this motivates why surface characterization of such structures is important, is relevant, especially since these nanostructures have a very large ratio of surface to volume. And also means, what are effects at the surface? If you think of electronic effects such as band bending or things, they can penetrate easily something like 50 nanometer into the material. And if the nanowire itself only has 40 nanometers diameter, so the entire structure can be considered as surface related or surface area, at least from this electronic point of view. And of course, all chemistry, all catalytic effects and so on, they take place at the surface. So it's important to characterize the surface of these structures in order to understand better their performance and in order to enable better devices. How can surface characterization be done? If you really want to go to the limit of resolution, so if you want to see individual atoms, since these structures get smaller and smaller, of course, it matters how they are really looking at the atomic scale. And the technique of choice usually for this is scanning tunneling microscopy, which I guess most of you know. When you have a conductive surface, you come with a conductive tip, scan it along, and measure the tunnel current which flows between your tip and the surface, which can give nice images like this here. This is an example for indium arsenide. You're also sensitive to chemical information with this. But the method has usually been, or has initially been developed for flat and clean surfaces. And we have something like the opposite structure here. If we have nanowires that have such a large aspect ratio, so how can we do STM on these things? Well, we could even do it on top, but that's not a topic for today. So what we usually do is that we break off these nice structures, that we put them onto a suitable substrate. This is an overview image here. Here's a zoom in AFM image where we have a single nanowire, in this case made of gallium nitride, so that we then can come along with our STM tip and position it here on a side facet of such a nanowire and scan the surface here. The next challenge is that these 3-5 materials, when they have been grown and are transported through air, that they oxidize. So we need to get rid of the native oxide on these surfaces, and that we do by annealing them in atomic hydrogen. And if that works well, we can resolve their structure, even zoom further in and see atoms on the side facets of individual of the structure. So if we here have the entire wire, what we are doing now is that we zoom in and go here on the side of one such facet here, and then we will see structures like this here, where we can see in this case, group 5 atoms here of gallium arsenide, indium arsenide, and phosphide, and you see the structures, different type of nanowire surfaces. The cleaning, of course, is a bit of a challenge. You can see here for indium phosphide, for example, we have some patches of native oxide left. For other materials, it works better. So after this motivation for why we want to use scanning tunneling microscopy, STM, and other surface techniques of these nanostructures, let me introduce the outline of this talk. So I will, after introducing this, I will focus on different heterostructures. So that is not only the nanowire surface by itself, but especially what's interesting is what happens if we have an interface towards, in this case here, another crystal structure. That is a special thing for these 3-5 nanowires, that they can have different crystal structures within one nanostructure. Beyond this, the surface topography will also look at surface electronics through spectroscopy. And we even show some examples that we can modify our surface. And then also we have used different type of interfaces like doping interfaces. And in the end, I will go towards device structures where we use STM even during operation of the devices. So getting started here, again, this is the surface of a nanowire, indium arsenide nanowire in this case. So what we can see directly from the STM images is something like the surface topography and also the crystalline quality. As in this example here, okay, you see nice areas where we can see these individual dots here, which are the atoms, arsenic atoms in this case. But you can also see the large number of lines here, which are defects. There can be stacking faults, that the crystal ordering is changed, or other type of defects. But what we also see is that this layer is entirely flat, in a large flat terrace, and that we have some islands here on top. And then if you have a very patient student who is sitting in the lab and doing image for image for image, you can end up with a picture like this. This is 36 individual STM images stitched together here to follow more than 3 micrometer of an entire nanowire with atomic resolution. And the interesting feature here was that we found exactly one monolayer high surface depth. So that was an absolutely straight nanowire in this case. But as I said, it becomes more interesting if we look at interfaces. And what is peculiar for these 3-5 nanostructures is that they can be engineered in such a way that you have different crystal phase in the same nanowire. This is an SEM image here, where you start after growth with the here, this is the catalytic growth particle. You start with the cubic structure, zinc blende. Then you can switch by changing the growth parameters. You can switch to a hexagonal wood-side structure, and then again it's cubic, it's hexagonal, and so on. These hexagonal structures are not even allowed or not even possible in bulk 3-5 semiconductors. So the surface structure was unknown. So it's only on these nanowires that we can resolve it. For example, here these wood-side 1,0 -1,0 surface facet, or these 1,1 -2,0 surface, which are different directions. And the zinc blende, the cubic structure, is more well known also from bulk materials, from substrates. If we then go towards a realistic surface here, this is the same area, only in 3D or in 2D visualization. This is an indium arsenide nanowire, where this here is the side facet, which is upright, where we can place our STM tip on top. So we come here with an hexagonal structure. You see here these zigzag lines that are individual atoms, which you can follow here, atom on atom. Then we come to an interface here where the structure changes from hexagonal wood-side to cubic zinc blende. We have a different pattern here of the atoms and the surface, and it goes back to the hexagonal case here. We also see some contamination here on the surface. And then we can go here across an edge. So this is a 30-degree angle towards a different facet at the side of this nanowire. And as I said before, in addition to the structure, which is maybe nice to see all the atoms are aligned, but if you want to use such a nanowire in an electronic device, you're interested in the electronic properties that you have here. So what we can also do then is that we perform scaling tunneling spectroscopy, where we can map, or we can image the local density of states. And the advantage of doing it on such a structure like this is that we can position our tip at the different places here, at the hexagonal structure, at the cubic structure, and back at the hexagonal structure. And so we can be sure, without changing our STM tip, which can give different electronic properties as well. So staying in the same conditions on the same surface, just by moving across the interfaces, we can compare the electronic footprint of the different structures. And this is how that looks. This is raw data here, where we measure the differential conductivity, so the derivative of the current. Why do we that? Because this is, which is shown theoretically, this is can be considered as the local density of state at the position of the tip. So what we get here, in this case, it was a gallium arsenide nanowire. What we see, if we start with a negative sample bias here, so we are tunneling with electrons out of the sample, filled states of the sample into the tip. So we are monitoring here, imaging the valence band until the valence band states vanish because we're reaching the band gap. Then we have no states here within the band gap. We see even some dopant contributions here. And then when we go towards positive bias, so now we are tunneling electrons from the tip into the empty states of the sample. So we are probing the density of states of the conduction band. And in STM, or scanning spectroscopy experiments, the Fermi level always is positioned exactly at 0 bias. So if we then compare these two spectra here, one taken from the wood-side hexagonal structure, one taken from the zinc blende cubic structure, you see directly by comparing them that there's a shift between the two spectra. So there's a band alignment between the two structures. And if we reveal that, analyze that properly, we see here that there is a conduction band offset between the two. It's the same material, only different crystal structure, only different stacking of the atoms. Still, we have a barrier here between the conduction band of both structures, both phases, of more than 200 millielectron volts. So that is a strong barrier if you want to have electron conduction through this nanowire. And this is called the type 2 heterostructure, since it's like a staggered, so both the conduction band level minimum and the valence band maximum are shifted in the same direction. Then the question came to us, since the structural transition can be very sharp, it can be at the atomic level, how well can we resolve the electronic shift, the transition between the wood and zinc blende, also electronically, or how well is it defined, even if you have very small structural changes? So we went to, in this case, we went to low temperature measurements so that we have a better stability. This was done in the Brookhaven National Lab in US. This is an indium arsenide nanowire. Again, these lines that you see here, these are atomic chains, arsenic atoms that we see here on this indium arsenide nanowire. This is one facet here where we have two terraces of different height. Then we have the edge and we have the other facet going down 30 degrees. This is a hexagonal structure, but if you look very carefully, you can see here there's kind of a stacking fault. So transition, the smallest possible transition of the crystal phase, because here we have two atomic layers of zinc blende, of cubic structure within this otherwise hexagonal structure. So let us zoom in here with the STM, and at these imaging conditions, we see the atoms of the cubic structure with a slightly higher density of state. So they are lighting up here in this image, as this is along the nanowire growth direction. So we see the individual arsenic atoms here, and then we can take spectra, tunneling spectra, directly at these stacking fault, as it's called, at this insertion here with cubic structure, and 2 atoms further away, 4 atoms further away, 6 atoms further away. So we can really go step by step, atom for atom, and look at the electronic fingerprint here of these structures. So if we do this for these positions here, which are within the matrix structure of the hexagonal phase, and we look at the density of state at these points, it has comparable features. At least we have some peaks here at more or less the same energy. We have the band gap. We have it looks similar, comparable at least. And if we then go directly to this atom here, which is within the stacking fault, so in the different type of crystal arrangement, we get this blue spectrum here, where we see some peaks, which you do not see in the structure around. We see a plateau where we instead have a steep increase of the density of states. So it looks quite different from the area around. And if we now compare these two atomic layers thin material here, the stacking fault of the cubic zinc blende structure with a bulk zinc blende structure of the same material, you see that we get the same peaks again and a similar behavior. So this is kind of the evidence here that even this only 2-layer thin structure has the same electronic property as the bulk zinc blende material, and that we even electronically, material switches between one structure to the other within less than a nanometer. And since this is such a small insertion here, we also see quantization effects. If we derive from the spectra that we see, derive the band edges, both for the conduction band here and for the valence band. And we do this, so we have here around the wood side, the hexagonal structure. And in here, this is a relatively large zinc blende structure. Then we can see again this band alignment. We are, in this case here on this indium arsenide, we see a band offset at the valence band side for 80 millielectron volts. But if we then go to smaller wood side structures as we have here, so if we have a double bi-layer zinc blende, so 4 atomic layers thin, we get then the apparent band difference, energy difference is smaller. And if we go to the smallest possible insertion, a single bi-layer zinc blende structure here, we get an even smaller energy transition since we probe here the quantized states. So we have quantization energy here in these quantum wells within our nanowire. So our stacking fault here, just the different transition of how the atoms are stacked, behaves like a quantum dot or quantum well, but in this case, in the nanowire around. Okay, let's go one step further, leaving for a moment here this electronic characterization. Until now, we only looked at the structures as we got them from the growth experts. We're not growing them themselves. We are only focusing on the characterization. But now we wanted to see what happens if we modify our surface. What happens if we dose some additional atoms from a different material on the surface? And again, we have in this case, it's gallium arsenide nanowire with different crystal structure, different crystal phase. We can zoom in here. So we see here the arsenic atoms in the cubic material. Here's a small insertion of hexagonal structure and cubic again. And then we anneal this surface in an antimony-rich environment. And what we see is that we get incorporation of individual antimony atoms. So these bright spots here, these are antimony atoms, which are seen a bit brighter due to their different size and different electronic properties. And if we count them, we see we have many more of these bright spots in the cubic material here and less of them in the hexagonal material. So it's a factor of 4 higher incorporation in one crystal phase compared to the other. Again, it's the same material. It's only a different ordering of the atoms, which results in a different incorporation of our so it's always they are built into the lattice of the antimony atoms. Here's it's visualized in different color, and this can be explained by surface energies, by the diffusion energy that it takes for an antimony atom to move along the surface until it gets incorporated into a possible lattice site. It was done by density functional theory in the group of Professor Kratzer in the University of Duisburg in Germany. After looking at antimony, we went one periodic table and even went to the even larger atoms of bismuth. We have a similar situation here. So we dose just less than a monolayer of bismuth onto a clean surface of gallium arsenide nanowire. We see here on the cubic structure zinc blende that individual atoms get incorporated here. They are clustering a bit at the edges, but they are at random positions on a clean flat terrace. But if we instead look at the hexagonal part, the both side part, we now see that we get in a self-aligned way or a self-selective way even, that here we, in this crystal phase, we get nice islands or these chains here. So the bismuth atoms now tend to arrange themselves into closed structures, evolving from the step edges here. So the bismuth atoms, the orange one, arsenic, and they are in the same atomic level. It's just that the bonds towards the bismuth are slightly longer. That's why they stick out a bit. And that was proven if we look zoom deeper in here in the surface. These are again all these spots here are arsenic atoms. The few bright spots are bismuth atoms, and you can see here the height difference between them is 50 picometers, so much less than the volume of an atom. So it's atoms which are incorporated in the lattice, but they are just sticking out a bit more since they are larger. Okay, so let's at this point now leave our crystal phase heterostructures and instead go to doping heterostructures. So what we have here is indium nanowires, which are aimed for solar cell application, as I have shown in the motivation. So we have nanowires which at the bottom part are p-doped with zinc, and in the top part are sulfur-doped, or n-doped with sulfur. If we look at them in an SDM image, in this case here, we have the catalytic growth particle that we see strongly, but then we have a rather thin and long nanowire at the surface. If we zoom in and take many spectra here, tunneling spectra, and plot them point by point, so that we see now the density of states at each position here in energy, and do this across the interface, across the PN junction, we can see here, visualize how we get the transition from n-doped Fermi level closer to the conduction band to p-doped Fermi level a bit closer to the valence band. But you can also see it doesn't look strongly doped here. The Fermi level is still within the bandgap, and we have here 2 examples of spectra in the n-doped area and the p-doped area. And the potential, the built-in potential, so the shift in energy between them is only 0.5 electron volt. On the other hand, we know the bandgap of indium phosphide is 1.3 electron volt, and these structures work as solar cells where we get an open circuit voltage of 0.9 volts. So we see it's important to look at the surface, because here we have different electronic properties than we have in the bulk, if one can say so, for a 200 nanometer thin structure. So on the inside of the nanowire, we have a larger bandgap than what we have here at the surface due to band bending towards the surface. We can look at the same type of structure also with an atomic force microscope, where we just see the topography of such a nanowire, and then also use Kelvin probe mode, where we, in an AFM, probe the surface work function. And even in there, you can see a transition here from the p-doped part to the n-doped part. And if we take a line profile here, we see that, oh, in this case, it's only 0.3 electron volts. It was 0.5 before when we did looked at it with scanning tunnel microscopy, only 0.3 with the Kelvin probe here. And that's because Kelvin probe operates in air. So we have the sample is oxidized, we have a humid environment, so we have even stronger band bending effects, and the built-in potential at the surface is even smaller as compared to the ultra-high vacuum conditions of the STM. And as an yet additional technique for complementary characterization, we use photoemission spectroscopy and microscopy. It's a special photoemission setup at the synchrotron Electra in Trieste, where the incoming photons are focused into a beam of only roughly 100 nanometer in size. So we can then scan the sample through the beam and look at the electrons which are emitted from our sample. The sample consists here of a single pin-junction indium phosphide nanowire, which is put on two gold contacts with a trench in between. So we're choosing at which element we look now. We get element-specific contrast here. If we choose to look at the gold, we can see lighting up here our electrodes shadowed by the nanowire. If we look at phosphorus, we see the wire, or if we look at indium, we see the nanowire. And of course, we also can then take spectra from the nanowires, photoemission spectra at the n-doped part or at the p-doped part. So we can look at the indium or at the phosphorus, and you can see a shift in energy between the n-doped and the p-doped part for both elements. And that is because our core levels that we probe when we do photoemission spectroscopy, they follow the band bending of the conduction band and valence band. So we can measure the built-in surface potential here, which is in this case with this technique again amounts to 0.5 electron volt. And why do we put this wire here on the separate contacts? Well, our aim also was to go towards device properties. So we apply now a bias between both contacts and see how the bias drops along the nanowire. So we have our p-junction bias either in forward or backward configuration. And then we take spectra along the nanowire point for point for point, what the resolution allows of this beamline. And without any applied bias, we can see the inbuilt potential as the shift of the spectra here when we go from n-doped or intrinsic area or the space charge region to the p-doped area. And if we then apply a forward bias, we see that the potential even increases the potential difference. If we have a backward bias, the potential decreases. So we can read out here how locally along the wire the forward-backward potential changes the alignment and where the applied potential drops along these nanostructures. We would like to also use our STM, coming back to our STM lab, for looking at device structures, and not just at prototypes which are easy, or model systems which are easy to look at, but also looking at realistic structures which are made to be used in devices. So the first challenge then is that we need to navigate to a specific area on a large sample. What you see here is an SEM images of a large device structure. So we have here something like 2 millimeters. And there's a processed area inside here where we have indium arsenide nanowires. So we zoom in here. We see this part. We see some markers here. We have to zoom in again in this very small area. And then what you see here is that we have laterally grown indium arsenide nanowires on top of an indium phosphide matrix. So this is SEM images. We then we take our STM tip. move along all the markers, try to find these structures, and yes, we got there. We can image them. So these nanowires here, which are grown laterally on the sample between two contacts, we can zoom in on the surface of such a single nanowire, which are about 60 nanometers wide here. And then again, we can take a spectra. We can look at the local density of state at individual positions. And we can see here, there's a change of the bandgap, there's a change of the density of states as we move along such a single nanowire. So when we are here in the center of the structure, we have the smallest bandgap. If we go a bit along the wire, the conduction band appears at slightly larger energies. And then if we go to the contacts, it's an even larger bandgap. That's due to two effects here. One is that we have different materials. So it's indium gallium arsenide, and we have a larger gallium content here at the contacts than we have inside the wire. We have a gradient here, but we also have strain in the wire, which works in the opposite direction. Now, to bring these together, until now we have looked with our STM at nanowires which are just lying on a conductive surface, and in most cases they were just randomly dispersed. So as we said before, we would like to look at nanowire devices, and ideally we would like to do this while they are biased. So while we put a bias across our nanowire heterostructure. If we want to do that, then we of course need to replace our conductive surface with an insulator. Otherwise, we would shorten the device. But if we have an insulating surface here, we cannot use STM anymore. So what we can do, we use what is called Q+, a tuning fork tip. So it's a STM tip here, which is mounted on a tuning fork so that it can be operated both in tapping mode AFM, or it's not tapping mode, it's non-contact AFM operation, or in STM operation. So we start getting an overview here, finding our structure, looking for it in AFM mode. So what you see here is this tiny nanowire and some large gold electrodes, which were defined on it lithographically before. So we see here that's the titanium structure of the electrode. If we zoom in, then we have our nanowire, which in this case consists of an actual heterostructure. So we have an indium arsenide part here and a gallium antimonide part there. So this is the SEM image of the structures when they were still grown, these nanowires. So we have an indium arsenide bottom segment, gallium antimonide top segment. And these nanowires are actually grown to act as an Esaki diode or a tunnel diode. So we can measure now in the STM through the context that we have here, through the metal context, the transport curve, the IV curve of such a device, and see, yes, we get this negative differential conductance. So we actually have a tunnel diode here, which is due to the expected band alignment between the indium arsenide and the gallium antimonide. But if we now switch to STM mode, so once we are on top of our nanowire, we can switch to we know that we are on a conductive ground, so we can switch to STM mode, take SDR spectra, and we see, oh, our spectra more or less overlap here in energy. So this structure that electronic footprint that we see at the surface would never correspond to a tunnel barrier as we have here. So again, the surface is different than the bulk inside. This was also confirmed by photo emission microscopy and spectroscopy, because we have a surface layer here of quaternary surface layer, which goes along the entire nanowire. But still, we can, with SDS, move our tip along the nanowire from the gallium antimonide part into the indium arsenide part, and we can see here, oh, there's an area, a depletion zone here in the middle, which is while it still works as a tunnel barrier. And then we can apply a bias, and what we plot here is the topography information. So we have the interface between the gallium antimonide, which is slightly larger in diameter at the indium arsenide, and then we plot the position of the Fermi level at the different areas. And if we don't apply any bias, it's the same potential everywhere. If we now apply a negative bias to the indium arsenide part, we have a sharp drop of the applied potential at the material interface, because this is now where the highest resistance is. If we instead apply a positive bias to the indium arsenide, we have a forward direction for this material junction, and instead the applied bias drops at within the gallium antimonide part, which now has the largest ohmic resistance within this entire circuit. Still, the limitations here in this approach are that we need to have this lithographic context. we need to use these Q+ tips in the AFM mode, which is difficult. So we would like to instead use an approach, use a structure where we can directly use our STM tip. So our next generation of device measurements then add a structure like this, where we take a silicon wafer, and we locally put some insulators on top, put a metal contact again, which can be externally contacted by thin wires, and then we place our nanowires on these metal contacts. So when our STM tip comes now from top, it either sees the semiconductor, or it sees the metal contacts, or it sees the grounded silicon. So it always has some conductive material where it can walk on. And with this structure, we could realize that we apply to bias here 3 volt source drain bias between both ends of the gallium arsenide nanowire, and still could get atomic resolution. And furthermore, we could even see an effect called electro migration. So what we see here is again the side facet of a nanowire. Gallium arsenide, in this case, we have some defects here in the surface. So we imaged it several times again for over 20 minutes, and the surface doesn't change. But if we now apply a source drain bias along the nanowire and image again afterwards, we see that some of the defects now have filled, some steps have slightly moved. So we have a migration of individual atoms here due to the applied bias. And in our latest version of these device structures, we want to be able to deposit a single nanowire between these contacts. So what we do now is that we define these contacts lithographically. Then we come with a nanoprobe, pick off a single nanowire from a gold substrate, take it with the nanoprobe, and deposit it on our electrodes, so that we then really have a device with one nanowire bridging the gap of our 2 contacts, so that we then can combine IV transport studies through that wire and STM studies along it. And this approach is still what we're still working on right now. There's a PhD student working on this in our STM lab, trying to get some first combined transport and STM studies of this approach. With this, I want to sum up my presentation. I hope that I could give you some glimpses, some impressions of how scanning, tunneling microscopy, and other surface methods can be used to characterize nanostructures, in this case our 3,5 nanowires, where we can compare atomic surface structure with local electronic properties, even about doping and material composition, and even do this on device structures under operation. I want to thank many people who are involved in this. First of all, I want to thank the organizers of this very nice conference workshop for inviting me. I want to thank all our current and former PhD students and postdocs who've contributed to the measurements. Also my colleagues, Anders Mikkelsen in Lund, Chris Palmström in Santa Barbara, where some of the images were taken. We have collaboration partners for theoretical calculations, and a lot of people who grow and process these structures in our collaboration within the NanoLund Center of Nanoscience at Lund University. And with this, I thank you very much for your attention, and I'm open for questions. Thank you.
Thank you very much, Dr. Timm, for this impressive work and amazing presentation. I can see one question in the chat area. Mr. Kamaljit is asking what is the difference between Acm and Stm. I think this could have been clarified during your presentation, but just for more clarification to the participants, if you could explain one more time the difference.
Yeah, sure. I'm sorry if that was not getting clear so much in the presentation. Well, SEM is the standard technique, scanning electron microscopy. It's a standard technique which is in many labs, where you have an electron beam, which from far away from the sample is focused on the sample, scanned on the sample, and you look at the backscattered electrons and get an image from the secondary electrons, which can nicely show topography, but not much more than topography. I mean, there are other methods available, yes. There is scanning tunneling microscopy, that is such a scanning probe technique, so where you really are in very close contact to your sample. So you have a few angstrom above the surface, where you move your probe along the surface and measure the tunneling electrons. So with that, you are again sensitive to topography, but you're here only sensitive to really the surface structure. There is scanning electron microscopy, probes an entire structure that you see. Here we only get our signal from the topmost 1, 2, 3 atomic layers, and we can look at the density, local density of states as well.